Welcome back. So, right now we're going to go through chapter 4 of this book, which is about estimating optimal portfolios. You can think about that CAPM, right? Before that, you formed the portfolio, efficient portfolio, right? And you were remember that umbrella like that graphs, and then you want to dot every possible portfolios based on those stacks, where the x-axis is the portfolio's risk, right? Volatility of the return, and then of the portfolio, and the vertical axis is the expected return of the portfolio, and then you have this kind of or in your side, right, this kind of graph, or this kind of shape, right? And then you remember at one point we were talking about the tangent portfolio, which is your efficient portfolio, and then there is a portfolio with minimum variance. Here it is risk, and then there it is return, and then minimum variance portfolio was there, and then the efficient portfolio was on the other side. This is risk-free rate, right? And all this kind of stuff. And how do you draw this kind of graphs, right? We're going to do that in this class, right? Okay, so let's go. From this, right, objective is earning the maximum return for a given level of risk, or building a portfolio with the lowest risk for a given target return is our objective. Estimating optimal portfolio has become routine thanks to this software. Empirical studies tell us that minimum variance portfolios tend to beat conventionally optimized mean variance portfolio, that tangent portfolio. But it's very strange and one of the big puzzles in finance. It is deeply related to the idiosyncratic volatility puzzle in behavioral finance, and part of it is explained by short sale constraint. So for overvalued stocks, you cannot short sell easily, so that it takes more time for that to correct. And then when it gets corrected, the stock price crashes. Okay, very big negative magnitude of return happens. Whereas when the stock is underpriced, right, you can easily buy it because there is no restriction about buying. Okay, short sell versus buying, there's an asymmetry going on, so that bubble takes place on average, and then more crash happens on average, so that the absolute return, right, I mean the return wise, right, negative returns happen more significantly in magnitude, so that more volatile stocks, more idiosyncratic volatility stocks, they tend to suffer from those kind of bubbles and crashes. So that is driving this kind of result. Minimum variance, minimum idiosyncratic volatility stocks, they tend to have higher returns. That's the thing over here. But anyway, in both US and international markets, futures stock returns or future stock returns of previously low return volatility portfolios significantly outperform those of previously high return variability. And then these findings are intriguing because economic theory dictates that higher expected return compensates for higher risk. The optimization methodology is still required to create minimum variance portfolios. So first of all, we're going to go through some hard ways to achieve this optimization process to get to that optimal portfolio. And then afterwards, we're going to go through a very easy way using our packages. But anyway, let's focus on 6 sets of monthly returns in managers data that we've been playing with in our performance analytics package, which comprise performance data for 2 hypothetical hedge funds, HAM, AF5, and 6. EDEC long-short hedge fund index, the S&P 500 index, 10-year treasury note, and 3 months treasury bill. Because the start dates vary, the first step is to create a data set with an equal length for all the time series by removing the NAs, the resulting return file, RET, reflects returns that run from September 2001 through the end of 2006. So I install those packages and then retrieve that data. Let me shrink down. All right. And then let's go. Yes. Now use quadratic programming, okay? Quadratic programming library via the solve.qp quadratic program, right? Command, right? But in the interest of illustrating the concept, solve QP is worth a short review for readers' interested in getting into the weeds in the corner of financial engineering. There are 5 arguments in solve.qp that are relevant for the toy example of building a minimum variance portfolio. First is DMAT, which is covariance matrix. Second is DVEC, which is a vector of the average return for each asset for calculating MVP. The vector is set to 0 for all the components. And the third is AMAT, which is a matrix of constraints, if any. And then the next is BVEC, which is a vector of values to impose constraints. And then the last thing is MEQ, instructions to solve QV, instructions solve QP to address the first X constraints as equality statements or not if set to 0. So we run this guy to create covariance matrix and the number of columns, and then create matrix of zeros and create matrix of ones, and then we retrieve this quadprog package. Then we run this MV portfolio, okay, which is a solution to this kind of that satisfies all these constraints stated above. And then MV portfolio weight will be calculated, and then it says round your results to the nearest 2 digits below 0, below decimal point. Now right, row name, column names, and then MV portfolio weights are shown over here to satisfy the minimum variance optimization. MVP weight column names shown like this. Oh, I should have written this like this. Yeah. MVP percentage weight, you see disproportionately or absolute majority of the weight is given to 3 months T-bill. Of course, it is the safest asset. So minimum variance, tells us to heavily load onto this 3 months T-bill. The optimization weight solution is captured in mv.port, which contains 6 objects produced by the quadratic programming. To list the objects, use structure mv.port. To extract the weight saved as the solution object, see the MV port solution output. And then to extract the weight saved as this. And then it's clear in the example above that the extreme weights are permitted. The 3 months T-bill allocation assumes nearly the entire portfolio with a near 99% weight. In addition, the solution allows for short sales, which is minus sign over here, short selling HAMS 5 and 6, and then S&P 500. Okay, a negative weight means short selling. Let's rerun. Okay, the number of limits limit the results. Number and limit the results to. Let's run the numbers and the results to long only positions. So you don't like short selling, then let's give some more restrictions that you cannot assign negative numbers in the weight. Okay, the adjustment requires 2 changes. First, the file for AMAT argument must be modified so that a diagonal matrix of ones is added. Next, a vector of zeros is added with a lead value of 1 in the BVEC. These changes are needed to compute the necessary matrix multiplication so that each asset weight is greater than or equal to 0. I should have said this. Okay, so we run it, and then following leads to value of 1. Yes, and then yes, no short portfolio looks like this. So it gives me that 98.8% should be invested in 3 months T-bill, and then only small tiny fraction of it on T bond 10 years, and then only small tiny fraction upon EDEC fund. Okay, let's add another constraint: minimum weight of 10% and maximum weight of 50%. Here we have extreme, which is almost all of them in a 3 months T-bill, but maximum 50%, let's put it that way. And 0%, no, at least 10% or something more. Okay, that's going to be our added restrictions over here, right? And then once again, we need adjust a mat and BVEC to perform the appropriate matrix multiplication for imposing a second level of constraint, right? And then do it like this, and then all is yes, right. Now it tells us that the portfolio weight has to be 46% on 3 months T-bill, 13% in the 10-year T-bond, and then the rest of them 10% each on the more risky assets. This time, the output provides reasonable, if still moderately lopsided assets. Mix skewed towards the 3 months T-bill. We could, of course, continue to fiddle with the constraints for something more appealing. Now the next is the easy way for optimization. An easier and far more flexible R solution for estimating the efficient frontier, including MVP, minimum variance portfolio. Let's rerun the minimum variance numbers in the previous example for comparison. This time, just optimizing portfolio package is optimizing in F portfolio package is good enough. Also, you need to install F assets and the DE Optim R packages to do all these things. So install and then trigger it with library. Yeah. Yes, it's busily installing it. Now we need to format return as time series object, and then use this right. Number of columns are designated, and then now let's set the parameters for the portfolio designed by using the F portfolio commands. Minimum weight of 10% for each fund, with a maximum being 50%. So, right. Computing the minimum variance portfolio weights and extracting the data from the output file works like this. Minimum variance, constraints, and then round it up to second digits after decimal point. You can also compute the entire efficient portfolio frontier. Efficient frontier with F portfolio, and then EF frontier will take that. Now what is that? It shows up like this. Okay, and then if you run plot EFF frontier, you will be prompted to select one or more charting options for the graphing of the portfolios, efficient portfolio, and related metrics. Okay, so I run it. Okay, and then ESC, escape button, will take you back there. Now I have a choice. One, plot efficient frontier. So I click one. Okay, it looks like this. And number two, add minimum variance portfolio, which is going to be over there, right? And then add tangency portfolio. That's three. Yeah, something, a tangency portfolio right behind, right above, right? Minimum variance, slightly different. Equal weighted, what is that? Add risk return of a single asset. Okay, you see dots, dot somewhere. And then 5 is equal weights portfolio. So you, yeah. And 2 asset frontiers, right? It draws at frontiers based on the 2 assets, any 2 combination of any 2 assets, right? You see these umbrella shaped, right, curves showing up. Okay, 6, that's the 6. 7 is what? Monte Carlo portfolio, so it will dot randomly that satisfies this constraints like this. Okay, so this is the umbrella shaped graph that you've been looking at in the typical textbooks. Monte Carlo portfolios, random portfolios within this constraint. And then the 8 is Sharpe ratio, right? Sharpe ratio, yeah, Markowitz portfolio only, but this one is not shown up. Okay, fine. So that's that. Escape. I just go there, punch in, and then I just get out of it. Here we can customize a portfolio based on various weight constraints via F portfolio. Let's compute the MVP with a 10% minimum, 50% maximum limit for each fund, with a combination combined 35% minimum, 45% maximum for the 3 hedge funds, HAM 5 and 6 and EDEC. To make this change, right? To make this change, create a new minimum maximum file to pass to minimum variance portfolio to reestablish with its weight. Okay, so give a constraint like this, and then minimum variance constraint -1 should be minimum variance portfolio based on it. Okay, and then round the result at the 2 decimal points. Okay. Now, F portfolio offers several options for customizing, including a spectrum of graphs, capabilities. You can generate an efficient frontier chart with a EFF.frontier object from above using tailored frontier plot, and then or create a weight plot via weights plot. For a complete list of graphics capabilities, see the reference manual. Okay, so like this. So this graph shows us at each given point in the x-axis of a target return. It tells us what has to be the weight upon each specific assets that you see. At the lowest level, you have to be heavily or entirely loaded on 3 months T-bill. At the other extreme, you have to be loading on to the other the hedge funds product, right? Portfolio, and then it gives you the weight like that. Okay, quite an interesting figure. All right,